Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we were talking about rotational kinetic energy. And we said rotational kinetic energy, it is the energy of something due to its rotational motion. It was measured in joules because all types of energies are measured in joules in here. And then after that, we talked about the law of conservation of mechanical energy. Prior to that, we said mechanical energy, previously, it was equal to kinetic energy plus potential energy, that is for translational motion. But this year, because we're dealing with rotational motion, we have another extra or another type of energy, and that is kinetic energy of rotation. So now mechanical energy that we have this year, it is kinetic energy of translation, kinetic energy of rotation, and also potential energy as well. And then we talked about the law of conservation of mechanical energy. We said mechanical energy at the top, let's say, of an object at the top of an incline, it is equal to the mechanical energy at the bottom. If we assume that there is no energy lost, and that is in ideal cases where there is no friction, where there is, or we say no energy is lost due to friction, let's say that way, and then if there is no air resistance as well. So if that is the case, mechanical energy, both initial and final, will be equal. And we also said that all the questions that we have, they ask about the, or at least one way or another, requires the translational energy of the object at the bottom of the incline. So if an object is falling down here, or rolling down rather than falling down, then the translational speed at the bottom of the incline, first of all, let's just say mechanical energy initial is equal to mechanical energy final. And then if you do the calculation, you will end up using or having this equation, V final, for translational, that is 2gh1 plus c. We said c stands for the shape that we have. Could be a ring, the disc, or the thin spherical shell, solid, well, doesn't matter. That is the equation that we use if the object is rolling down, don't forget. But if it doesn't roll down, like for example, if it is falling down, then the equation becomes what? V translational or V final at the bottom, it is equal to what? It is equal to 2gh only. So regardless to whatever the shape that is falling down, all of them would have the same translational speed. And we also said that if the object is falling down, their translational speed would be higher than if they are rolling. And the reason why, because part of that energy converts or changes to rolling, so the object will end up with a less translational speed at the bottom of the incline. And that is, we solved two questions there. Now we're going to continue with this, but the question that we have is a little bit the next one. We said we need the height of the object, and also we need the shape of the object as well. These need to be, or needs to be, known in order to do the calculation correctly. We have a question here. For this question, the height is not given, or the height is unknown. So first we'll have to find the height of the object, then we could do the calculation here. So what does it say? The object, or the question says, a regulation basketball has a 25 centimeter diameter. Once again, if you just find, or if you just need translational speed, you don't need the mass or even the radius. But if there are other requirements, then you have to be careful, say if you need them or not. So here says a regulation basketball. Remember the shape or the moment of inertia for a basketball, that is considered as a thin spherical shell, and the moment of inertia for a basketball, it is 2/3 mass times radius squared. At this point, we just need this factor here. Remember, we call this one C. Okay, that is first. It says this is a diameter, which is 25 centimeter diameter. It may be approximated as a thin spherical shell. That tells you that. The question says, how long does it take the basketball starting from rest? Okay, starting from rest. What does it mean starting from rest? That means V initial, or let's just start with this one here. It says, how long does it take? Isn't that delta T here? So how long does it take? That would be delta T. All right, that is the first thing. The next thing that we have, okay, that is delta T. So starting from rest, that means V initial is 0. Don't forget. Without slipping, a 4 meter down an incline. Now I really need you to know this one here. So once again, let me write this. Delta T, it is unknown. They ask for this. Starting from rest, that means V initial is 0. But then it says this thin spherical shell, it is rolling down without slipping a 4 meter down an incline. Now, of course, because you're studying in the English system here, so down the incline, what does it mean? That means is this the height of the incline or the length of the incline? Clearly, that is the length of the incline, so be careful at this point. So the length of the incline, we can say delta x, it is going to be 4 meter. So if I draw this one here, so let's just draw a little bit lower. That's what we have. So a basketball, this is the length of the incline here. You can call it delta x, and this is 4 meters. It's going to roll down here. So what do we want? First of all, we said you will need tangential speed one way or another at the bottom of the incline here. So obviously the height is not given. What else? It says down the incline that makes an angle 30 with the horizontal. Of course, you do know the difference between horizontal and vertical, yes? Horizontal, that'll be the angle with the x, and that angle is 30 degrees in here. So, but the problem is, we said earlier, or even the other lesson here, we need the height, yes? So how do you find the height at this point here? Of course, you could have done this one here, right? So how do you find the height at this point? So now let's expand the whiteboard and see how we could do this. All right. Perhaps, let me just make this one a little bit nicer maybe. Okay, that is, let's say, the length of the incline. That is 4 meters. This angle is 30 degrees. This is the incline here. So this is the thin spherical shell in here. So this height that is needed, it is unknown here. But how do we find the height? Well, let me tell you something here. We have 3 functions. Sine theta, we have cosine theta, and then we have tan theta as well, yes? So sine theta, it is equal to opposite over adjacent, yes? Opposite over hypotenuse here. Cosine theta, it is adjacent over hypotenuse in here. And then tan theta, it is opposite over adjacent. Opposite over adjacent. Now, if I want to be more precise here, opposite to this angle represents the height here, yes? That'll be the height over the hypotenuse represents delta x in here. The second one here, adjacent, that'll be this length here. You can say, whatever it is equal to, this horizontal length or whatever, divided by delta x in here. And then opposite, that is clearly the height over opposite over adjacent, which the adjacent is unknown here. Let's write the unknown here as well. You might still have no idea what I'm doing at this point here. So this is a question mark because these are unknown here. So here's my question. Which one of these functions allow you to find the height? Take a look. We have sine, cosine, and tan theta. Isn't that sine theta allows me to find the height? Yes. So what if the situation was different? What if you were given, let's say, the horizontal distance? Then, of course, you would have used the cosine theta to find this. If you were given this, let's say, and that, or whatever, then you could have used, what? No, okay. So once again, if you were given this, for example, and then the angle, to find this height here, you would have used tan theta here, just by any chance, for example. So my point, here is this. Always see which side is given and which side is unknown. Based on that, you can use one of these 3 functions to find whatever that is unknown here. So once again, at this point here, I need the height, and I can find the height by using sine function here. So I'll choose this equation right here. So the first thing to do, I'll use sine to do what? To find the height. Why? Because if I want to find the velocity here, I need the height, which I don't have the height. You might wonder, why do we need to find the velocity when the question is asking for delta time? I'll tell you in a second now. But whenever it comes to these questions, you can find the height anyway, because you will need it either cases. Okay, so at this point here, sine theta, it is equal to the hypotenuse, the opposite, which is the height over the hypotenuse, which is delta x at this point. So you can cross multiply. The height is equal to delta x times sine theta. So once again, delta x is 4 times sine 30. So the height is going to be, or it is equal to 2 meters now. So I have found the height, you can say this is the first step. The second step, I'll find the tangential, or V final at the bottom of the incline, tangential you can say, which is equal to square root of 2gh. That'll be V final, by the way, because initial is 0, the object started from rest, don't forget. 2gh, 1 plus v here. So once again, 2 times 9.81 times the height we just found, which is 2, 1 plus, what was the shape? It was a thin spherical shell or basketball here, that is 2 over 3. Let's do these numbers and see what is it equal to. That is 2 times 9.81 times 2, that is the height, 1 plus 2 over 3. 2 over 3. The answer is equal to 4.85. So the V final here, we can say, tangential final, it is equal to 4.85 meter per second. That is the final velocity at the bottom of the incline here. That is the second thing here. Now, going to what exactly the question wants. Says, how long does it take this basketball, thin spherical shell, whatever the shape is, starting from 0 to the bottom of the incline? Like we have V initial, we have found V final, which is 4.85 or 4.85, okay? Now, and we also have delta x as well, which is the length of the incline. So how long does it take to get there? Now, do you remember using the 4 equations that we've used? Because the object is moving in a straight line at this point here, we can use the translational or the 4 equations of motion to find how long time does it take. So let me just erase this part at this point here. So now we can say, to find this one, let's just increase this a little bit. Okay, so we can say one of the 4 equations, remember, delta x, it is equal to what? It is equal to 1 over 2 V initial plus V final delta t. See, this delta t here, it is unknown. That is what I need to find here. So once again, delta x, that is the length of the ramp or the incline, that is 4 meter here. It is equal to 1 over 2. V initial is 0. V final, we just found it, was 4.85. Now find delta t here. Okay, so you could cross multiply this two, that would be 8. It is equal to 4.85 delta t here. Okay, and then 4.85. So how do you find delta t now? Both sides divide by 4.85? 4.85 in here. So what is delta? These two obviously cancel out. 8 divided by 4.85. The answer is equal to 1.6 seconds. So delta t is equal to 1.6 seconds. This is how long it takes this thin spherical shell, the basketball, whatever that is rolling down, starting from the top of the incline to the bottom of the incline. How long does it take? It takes 1.6 seconds. And once again, why did I find V final here? Because if I want to find delta t, I need V final here. V initial was 0, so I need V final, so that because I have delta x, in order to use this equation, I have delta x, I have V initial, I needed V final so that I can find delta t here, and that's why I found this one. So whenever it comes to these questions, always make sure that you find V final because you will need it one way or another. So that makes it a lot easier to solve this question here. All right, so that was the answer to this question here. Okay. What else do we have? Now there's another question here. Says actually we've done this one before. It says a solid 2 kilogram ball with a radius of 0.5 starts from a height of 3 meter, rolls down a 20-degree slope. A solid disc and a ring start at the same time and at the same height. Both the ring and the disc have the same mass and the radius as the ball. Which one of these objects will win the race to the bottom if all roll without slipping here. And if you remember this, previously we said there is an experiment here. We did talk about this one. We said what happens if we have three different objects. One of them was, we can say a solid disk, or let's say a solid object here, solid object. And then the other one was, we can say a disk or hollow cylinder, a solid cylinder, and the other one was a hollow cylinder. In other words, the moment this is the same as a bowling ball. The moment of inertia for this one, it was 2/5 mass times radius squared. And then for this one, it is 1/2, and for this one, it is 1. Do you remember this? Okay. We said which one of these would roll or reach to the bottom first? We said that the solid ball or the bowling ball. And why is that? Previously, we were saying if moment of inertia is the largest, angular speed would be the lowest. In other words, if moment of inertia is smaller, then angular speed would be the fastest. So we said the moment of inertia for the solid ball, the bowling ball, is the least. So this one would reach the bottom to the incline first. And then after that, the disk, we can say, and then at the end, or the third place, would be for the hollow cylinder. Previously, we were just saying this, right? But now it is time to prove this using numbers to see if it is right or wrong. So each one of these have the same mass, the same radius, and they are falling at a height of 3 meters. So the height is 3 meters. So what are the equation that we use? Because each one of these are rolling down, so we can say V for solid sphere, it is equal to 2gh, which is 9.81, times the height, which is 3, divided by 1 plus 2/5, right? That is first here. What about for a solid cylinder here? V, it is equal to solid cylinder. It is equal to 2gh, that is 2 times 9.81. The height is 3. All of them are the same height, 1 plus 1/2. What about for a hollow cylinder? V for hollow cylinder, it is equal to 2gh, which is 9.81 times 3, that is the height, divided by, and that is divided by what? Divided by 1 plus just 1 here. So these two cancel out here, okay? And let's see what are the value for each one of those. As a matter of fact, we have the numbers already. You can see for the solid sphere, it is 6.48. So the answer for this one, let's use a different color, 6.48 meter per second. What about for the next one? It is 6.26 meter per second. And then for this one, it is 5.42. 5.42. So see the numbers in here. So we said that the solid ball, because it has the least moment of inertia, would reach the bottom first. Okay? And this one would be the last one, or you could say the third one here. And these are the numbers to prove that of what we have said earlier. So we can say the velocity of solid sphere, it is larger than, if you want to rewrite this one now, we can say the velocity of, let's go down here, the velocity of a solid sphere, you could say, it is larger than the velocity of a, we can say solid cylinder, which is larger than the velocity of a hollow cylinder here. And that's it. But if I rearrange their moment of inertia, we can say moment of inertia of this one, it is going to be the least. The moment of inertia for this one here is going to be larger, but the moment of inertia for the hollow cylinder is going to be the largest in here. So this will be the largest, then this, larger than this, and which is larger than this one here. That is previously, we've mentioned those in here. Okay. Solid disk or solid cylinder makes no difference here. Okay, so you could see the ball comes first, and then after that the disk, and then after that the ring. Now there's another question which is similar to what we have solved. We could give it a try real quick. If not, there's nothing special about this because the height is given. I have a suggestion for you, perhaps maybe after this. It's a 30-kilogram bowling ball with a radius of this much, starts from rest, so V initial is 0. At the top of an incline, which is 3.5 meter high. Always check if the height is given, if not. And then there is another thing just to help you double check. When angles are given, always double check the numbers that is given, because angles given could be an indication that the height is not given. But that is not always true, because the first question we solved in this section, of course, or in this concept, the height were given and the angle were given too. So just be careful once angles are given. Most of the time, if angles are given, double check the number. Perhaps maybe the height is not given. The question says, find the translational speed of the bowling ball after it has rolled to the bottom of the incline. So we said just one equation to do that. Tangential with translational speed, that is 2gh divided by 1 plus c. You have gravitational acceleration, you have the height, which is 3.5. You have c, which says a bowling ball. What is the c for bowling ball? That is 2/5, because that would be the same as a solid sphere or bowling ball here. All right. Now another question, which is also the height is not given, says what? It says a solid 240 Newton ball, that is the weight of a ball, which we don't need at this point, with a radius of, here's a radius. We said you don't need the radius for translational, but if there are other requirements, maybe. We'll just have to look what the question wants. It says roll 6 meter down a ramp. Once again, it says down a ramp here. That is along a ramp in here. So no height. Again, you can write this down something. That means along something here. So this is not along the ramp in here. So along the ramp, that is not the height. This is just the length of the ramp. That is inclined at 37 with a horizontal. If the ball starts from rest, so V initial is 0 at the top of the ramp, what is the angular speed of the ball at the bottom of the ramp in here? So find omega final. But first we said we always try to find V final, right? If you find V final, then clearly you can find omega final, because omega final, it is equal to V final divided by the radius here. So this will be the first step, and this is going to be the second step. So let's just solve this question together. But remember these steps in here. All right, so let's try it. All right, so what is given here and what is unknown? Okay, so the first thing that is given, it says a solid ball. What is the moment of inertia for a solid ball? Let's just write it down here. Moment of inertia for a solid ball, it is 2/5. Mass times radius squared. And here's a solid ball. Like a bowling ball here. Okay, it says rolls down. The radius is, let's just write the radius too, because we need it at the end for angular speed. It is 0.2 meter. Or 20 meter, rolls down, ramp that is 6 meter long in here. Let's just draw some shapes maybe. So here's one thing. The length of this ramp is 6 meter long in here. So we can say delta x, it is 6 meter long. Let's add one more point here. So what else? It says it is inclined 37 degrees. So this is 37. This height is unknown here. Okay. Starting from rest, so V initial is 0. What is the angular speed? So angular speed is unknown here. That would be final angular speed, because if V initial is 0, that means omega initial is also 0 at this point. Okay. Of the ball at the bottom of the ramp in here. So pretty easy enough, I guess, right? All right, so the first thing that we have to do is we have to find what? We don't have the height, right? So if I want to use this equation here, V final is equal to the square root of 2gh over 1 plus c, right? I don't have the height. So how do I find the height? We said we have 3 functions, sine, cosine, and tan. Which one of these allows me to find the height? That would be sine theta here. So we'll say sine theta It is equal to the opposite, which is the height, over the hypotenuse, which is delta x at this point. So the height, it is equal to delta x times sine theta. Delta x is 6 meter sine 37 degrees. So let's see, what is this equal to? 6 times sine 37. The answer is equal to 3.6 meter. So the height is 3.6 meter height. That is the height. After I have found the height, now we can bring this number into this equation here. So you could say, I don't know, the first step, second step, third step, back to this. Okay. So that is 2 times 9.81 times 3.6 we said, divided by 1 plus c. What is c for a solid pole? We said 2 over 5. That is 2 over 5. Let's find this one here. The square root of 2 times 9.81 times 3.6 divided by 1 plus 2 over 5. Whoops. The answer is 7.1. So V final is equal to 7.1 meter per second. But remember, this is translational speed. We don't want translational. What do we want? We want angular, correct? So how do you find angular now? 7.1. I guess we could just move it up. Okay, so omega final, that would be V final over the radius, true? 7.1 meter per second divided by the radius. What was the radius? 0.2. What is it equal to now? 7.1 divided by 0.2, the answer is 35.5. You can even round it up to 36 as well. 35.5, it is going to be radian per second, and that's it. See? Hopefully easy enough. Okay. This question is 2, which is also very interesting. It says 2 spheres look identical and have the same mass. This question is also Benunuzari as well, by the way. So there are 2 spheres. They look identical. They look the same. They have the same mass and the same radius. Clearly, if they look identical, they have the same radius and they have the same mass as well. So same mass and same radius as well. It says, but one of them is hollow. That means the inside of one of them is empty. There's nothing in it, but the other one is a solid. So one of them is solid, is filled, but the other one is hollow, it is empty. But because these are not transparent, we cannot see through. We cannot see which one is hollow and which one is filled or solid. The question says, which method would determine which is which? Which one of the following ways can help us to tell which one is the hollow, which one is the solid? So we can, let's just say, start backward at this point. The part C says if we weigh them on a scale. I mean, that's not how we're supposed to, but let's just, it makes it better. Like, it is more interesting if we start at C. Otherwise, it's not a good thing, actually, to start from option C. But if we do that, you see the difference while we did this. Okay, says weigh them both on a scale. Actually, if we weigh them both on a scale, because they have the same mass, would the scale tell any difference? Can the scale tell us which one is which? No, because tell them on a scale, it's the same as put them on a balance, on a, like a spring balance or whatever, because they have the same mass, so the balance would, of course, show no difference here, because they have the same mass. So option C does not allow or does not help us to see which one is the hollow, which one is filled. What about B? It says drop them from the same height. Well, if we drop them from the same height, didn't we say if we drop them, there will be always one equation, and that is 2gh. Okay, 2gh. So they will both reach or fall at the same speed at this point, or they reach or their final velocity at the bottom of the incline is going to be the same. So even this method does not help us to separate or to tell which one is which. That is this. What about option A? It says roll them down an incline. Well, that is the correct option, but what exactly happens if we roll them down an incline? We know that if we roll them down an incline here, they're going to roll, yes? So one of their equations is going to be 2gh1 plus c, right? That is this. And then the other one is going to be, let's use a different color here, is going to be 2gh1 plus c here. But the c for one of them, it is going to be what? The one that is solid is going to be 2 over 5. The one that is hollow, it is going to be 2 over 3. And because they have different shapes or different factors here, so their velocity is going to be different. Now we know that the one that reaches the bottom first here, that one, it is going to be what? It is going to be the one that is solid, because the hollow one, it would have less velocity at this point. And you could do the math yourself. For example, if it is at the same height, you could use any number. 1, could be 2, could be 3, doesn't matter. And then plug in the numbers. You will see that the velocity for this one, it is going to be higher than the velocity for this one here. Once again, the one that reaches to the bottom first, that would be the one that is solid. Okay? This is how we can separate the two. So this is what we started from C first, because this would allow us to separate, but dropping them, no. Weigh them on a scale, that is also no. This is the same as the previous questions, I believe. You could do that yourself in here. There's another question here, says, a 0.02 meter diameter coin rolls up a 15-degree incline. This one is a little bit different than the previous questions. All the previous questions that we had, the objects were rolling down, right? But this one is, the object is rolling up. It is going upward instead of going downward here. That'll be one of the key differences between what we had before and this one. Okay, so see what exactly the question wants at this point here. So it says, first of all, we have a diameter. Okay, what is the diameter? It is 0.02 meter. Okay, it says it is a coin. What is the moment of inertia for a coin? It is like a disk, which is 1 over 2 mass times radius squared. Perhaps we need this, 1 over 2. Let's just write this one a bit nicer. Okay, we might need this one. It says rolls up a 15-degree inclined plane. The coin starts with an initial angular speed, don't forget. So this is the initial, but it's not just translational, it is angular speed. So here's the initial angular speed, which is 45, that is radian per second, don't forget. It says, and rolls in a straight line without slipping. How much vertical distance does the coin roll before stop rolling? So how high will it go before stop rolling? Before stop rolling here, that means omega final, it is going to be 0 here, which is the same as saying V final is the same. See the difference between this and that? So let's just expand this one here and do this question here together. First, let's draw the diagram, see what exactly this one is. So here's an incline. There is a coin here. This coin is going to roll up this time here. And we want to know how high will it roll up. How much is it going to move upward here? Oops. Just do that one more time. Let's make it red. Okay, so this coin that is going to roll up is going to move, but we're just trying to see how high will it go up. This angle is 15 here. Let's just say you might stop at this point here. How high is this point here? Could be at any point, by the way. So this is what we have. So what we're going to do here is we're going to use the reverse of the previous questions. What do I mean by the reverse? Previously, we were using this equation. We were saying V final it is equal to 2gh1 plus c, yes? We had the height, we were finding v final, let's say how fast it was rolling when it was at the bottom of the incline. But the thing is, at this point here, we have the initial of the object. It is rolling with a certain speed in here. We just want to see how high it is rolling up. So in this case, instead of v final, we're going to make this one v initial here. Because that v initial, that'll be the speed of the object, like how fast it is going up, all right? And then so that we can find the height. You might say, what about v final? If I write v final, the whole thing is 0. So will that help me to solve the question? The answer is no. So I cannot use v final because v final is 0 already. So this is v initial, but there's one problem here. In this equation, it is v translational. What is given here, it is the angular speed. Can I convert angular speed to translational? The answer is yes. So how can I do that? We know that translational speed, it is equal to translational speed, it is equal to omega times the radius here. So omega, it is 45 times the radius. But do I have the radius? The answer is no. But what I have instead, I have the diameter. So what is the diameter? It is 0.02. How can I convert the diameter into radius? Just divide by 2, yes? Let's not forget this one here. So the diameter is, or radius, that is equal to diameter divided by 2. That is 0.02 divided by 2. It's going to be 0.01 meter. That is the radius here. So now just multiply by this, 0.01 meter. So the answer is going to be 0.45 meter per second, and that's it. So if I have v initial, the height is unknown, yes? So I can find the height. So v initial is 0.45. It is equal to the radical of 2 times 9.81. The height is unknown times the height divided by 1 plus c. What is c for a coin? It is 1 over 2, or you could just say 0.5. Makes no difference here. How about if I do all these numbers together here? If I do this, right, that makes the calculation way easier for me, yes? That would be 2 times 9.81. It is equal to this much divided by 1.5. So the answer equal to 13.08. 0.45, that is equal to the square root of 13.08 times the height. Now, how can I extract or get the height from this? Can I square both sides? Yes. If we square both sides, these two will cancel out. So 0.45 squared, what is it equal to? It is equal to 0.2025. What a number. Okay, and this one here is becomes 13.08 times the height. How do you find the height now? Just divide both sides by 13.08. 13.08. So we have 0.2025 divided by 13.08. The answer is equal to 0.0. So the height now, it is equal to 0.00154, you can say 155. That is in meter. Actually, if you're going to convert this one to centimeter, of course, you just multiply by 100, then that is going to be 1.55 or 1.6 centimeter by rounding here. But that would be the height or how much it is going to roll up before it stops. So at this point, when the height is 0.0155 meter, then this coin just stops rolling, and that is the answer to this question. Okay. And here's the fast way using this, but first you have to convert and all that. So there's nothing special about this one. And this is the long method if you want to prove that here. Okay. I think perhaps we'll extend this video a little bit because now we have another question here. This question is also very interesting. What does it say? It says a solid sphere rolls along a horizontal surface at a constant linear speed without slipping. Show that the rotational kinetic energy about the center of a solid sphere is 2/7 of its total kinetic energy here. So what do we have? A solid sphere. Okay, so we have a solid sphere. The question says, show that it is clearly moving at a constant linear speed. Show that it is rotational kinetic energy about the center of a sphere is 2/7 of its total kinetic energy. 2/7 of its total kinetic energy here. Now, of course, in math, you do know that when it says 2/7, that is 2/7. But before we solve this question, let me tell you some methods that can help you a lot with these kind of questions here. But I want you to remember this for now. Just for now, remember this. If I have kinetic energy of rotation, this is something very important, and I need you to pay attention to this. Kinetic energy of rotation, it is equal to 1/2 moment of inertia times angular speed squared, yes or no? And previously we've learned that moment of inertia, it is equal to what? It is equal to c times, or shape, that would be mass times radius squared. And for omega, it is equal to tangential over the radius. Tangential over the radius. But now we have to plug these numbers into the equation. That is for rotation. So kinetic energy of rotation, it is equal to 1/2 times c times mass times the radius. We've done this before. Squared times tangential over the radius, but because this is squared, so these are both squared and squared. These two cancel out. We'll bring the c to the front. So 1/2 mass times tangential squared in here. So that is translation, that is rotational kinetic energy. But watch this. You do know what is this equal to, right? So can I say, or whenever I have kinetic energy of rotation, if it serves the purpose, you can always write c times, what is this value equal to? Isn't it equal to kinetic energy of translation? Yes, I need you to remember this now. At any point, if you ever had kinetic energy of rotation, by any means you needed the translational kinetic energy, whatever, you can always write c times translational kinetic energy. And you do know what is c equal to, which is the shape for the object that is rolling down. Don't forget, that is only if there is rotational kinetic energy. So, at this point here, okay, instead of rotational kinetic energy, you can always write c times translational kinetic energy. Now, I need you to remember this. Masha, that's one thing. The second thing is, whenever we have ratios, whenever you have ratios, or you can say ratios only. For ratios only, that would be best if we do that. For ratios only. Don't forget, if it is not a ratio, it might not work. So anytime you have translational kinetic energy, you can write 1 instead. And anytime you needed rotational kinetic energy, you can just write c instead. And you know what is c? That is the shape, or you can say the factor for the shape for the moment of inertia. So now let's go back and see if we can solve this question for. The question says kinetic energy of rotation to the total, right? So if I want to kinetic energy, let me rewrite this. Kinetic energy of rotation to the total, right? To the total. Now I know that kinetic energy of rotation, that's what it is. For total, we have kinetic energy of translation plus kinetic energy of rotation, yes or no? Now apply the note that I just told you here, this note right here. For kinetic energy of translation, write 1 instead. For rotation, write c instead. So what would be the answer to this? That is c for rotation, because we're going to write this, or use the note here. For translation, that would be 1. For rotation, we'll just write c. Now, all you have to do, just know what is the c for. Remember, the shape was solid sphere, right? So if it is solid sphere, it's going to be 2/5, 1 plus 2/5. That's it. So now all you have to do, just do the math. But remember, you have to make it a ratio. So we have 2 over 5, 2 over 5 divided by 1 plus, again, 2 over 5. The answer is going to be 2 over 7. The answer is going to be 2 over 7. See how simple it is? And that is exactly what the question says. In Uzari, of course, you're not going to be proving anything, but they'll give you something like this. They'll be asking, what is the rotational kinetic energy of a solid sphere to it is total kinetic energy, let's say. So write whatever that you have, then you can simply find whatever that is been asked here. Okay, let's change the question here to some other things here. What if the question says, what is the kinetic energy of, let's say, what is the ratio of kinetic energy of translation, let's say, to, instead of the total, let's just say kinetic energy of rotation for a disk. Okay, so of course you'll be given some options here, but this is how you're supposed to do that. First, write the equation. It says kinetic energy of rotation, as a matter of fact, it says translation, my bad, to kinetic energy of rotation. So it doesn't have to be the total always. Kinetic energy of translation to the rotation, yes? We said for kinetic energy of translation, just write 1. For rotation, just write C. So now, 1 over, what is C for a disk? It is 1 over 2, yes? So just this 2 is going to go up, or you can take the reciprocal, so it is going to be 2 over 1. Okay, it could be for any shape, by the way. It could be rotation over the translation, doesn't matter. Translation over the total, doesn't matter. As long as it is a ratio only, don't forget, instead of kinetic energy of translation, write 1. Instead of kinetic energy of rotation, you can write C instead, and that's it. Okay, what if it is a different shape, by the way? So let's perhaps answer 2 questions and then come back to this one here. We have 2 questions, perhaps maybe actually 3 questions here. Okay, so this is the method that you have to. We have 2 Uzari questions here. One of them is question 44, and the other one is question 60, I believe. So let's go to these questions. Question 44. All these questions are for you to practice, so make sure you do them well. So let's answer this question here. Question 44. How about you give it a try before I solve this one first? Don't forget the rule. If it is a ratio only, if it is not a ratio, of course it could be different, and we have different ways for that too. So these are what we have. It says a cylinder rolls along a horizontal surface at a constant linear speed without slipping. What is the ratio of the rotational kinetic energy about at the center of the cylinder to its total kinetic energy? So what do we have? We have a cylinder. Okay. So what is the moment of inertia for a cylinder? You do know that. It says, but remember, it says rotation for the total. Well, that's the rotation for what? For the total. Here's the total. First, try to simplify this. Kinetic energy of rotation over total, which means translation plus rotation. Yes or no? But man, instead of every rotation, write C instead. And for every translation, write 1 instead. So what would it become? C, 1 plus C. Masha? What is the C for a cylinder here? We know that for cylinder, it is 1 over 2. 1 over 2, and then plus over 1 over 2. So just let's do the math and see what is it equal to. So we can say 0.5 if instead of that, divided by 1 plus a half. So it is going to be 1 over 3. This one is gone. 1 over 3. Which one is 1 over 3? So after you do the math, of course, you'll get 1 over 3. So the correct answer now must be option B here. That's how easy it can be. All right. By the way, they gave you this one as well, so you really have, you really don't have to worry about any of those here. But what if this is not given? Something like Question number 60. Let's go to 60. Which is also a very interesting question here. Question 60 says, it says, for which of the following object, this one you have to try to, like use different shapes at this point. Okay, here's question number 60. Okay, it says, for which of the following object during rolling, it is translational kinetic energy. Watch this. It is what? It is translational kinetic energy. It is twice that of it is rotational kinetic energy. It is translational kinetic energy. So here's kinetic energy of translation. It is twice of it is rotational kinetic energy here. So how do we set translational kinetic energy? Twice of that. Twice of that, it is, or it means that 2/1. Translational kinetic energy to rotation, it is 2/1. So what do we have to do at this point? You'll have to try to each one of these shapes just to see which one of this is this. But we've learned that for translational, we're just going to write 1, right? For rotation, we're just going to write C instead. So now let's try each one of these shapes and see which one of them it is equal to 2/1. A holosphere here. What is the moment of inertia for a holosphere? We know that for holosphere, it is 2/3. So if you simplify this one, this 3 goes up, it would be 3/2. That is not 2/1, so it is not the first one here. Now, what about the second one here? Don't forget, let's just write this one instead as well. So we said 1/c. So the first one, it didn't work, so it is not a hollow sphere. What about the second one? Solid sphere. 1/c. What is C for solid sphere? That is 2/5, yes? So once again, the 5 goes up. That'll be 5/2. Again, that is not 1/2, so it is not this one either. So it is not the second option. Now, what about, try the third option, solid cylinder. What is the C for solid cylinder? It is 1/2, yes? So this 2 goes up, it becomes 2/1, and that is the correct answer here. So the answer, it is C here. What about, let's try this one. It says both A and B, of course, these were incorrect. You might wonder, for example, sometimes if you memorize, for example, just numbers, you might face some difficulties here. For example, now there's another question. You might say, what if I have, these are all kinetic energy of translation and rotation, let's say translation to the total, or rotation to the total, or translation to the rotation, or rotation to the translation, doesn't matter. I hope you understood what I was saying. What if I have different shapes? Would it work? Again, yes. What do I mean by this? I need you to pay attention at this point here. I have a question like this one here. Let's just hide the answer. Take a look at this one. This is also a new idea. It says, what is the ratio of the rotational kinetic energy? Watch this. Of what? Of the rotational kinetic energy. So here's one. Of the rotational kinetic energy, but of a solid sphere to the rotational kinetic energy of a thin spherical shell. So this one is a bit different, right? But you guys don't worry. Here says rotational kinetic energy. Rotational kinetic energy for what? For a solid sphere. To what? To the rotational kinetic energy for what? For a thin spherical shell. Thin spherical shell. Okay, so remember, we said whenever you have rotation, just write C instead. Whenever that is C for this one too. But remember, we have different shapes, so you have to try different numbers in here. So for C, for thin or solid sphere, for solid sphere, it is going to equal to what? It is equal to 2/5, right? What about for thin spherical shell? It is 2/3. All right, now, of course, you could simplify this one here, or just, as a matter of fact, don't bother. just use a calculator. But at the end, you have to convert this one to a ratio. That is 2 over 5, Pasha, divided by 2 over 3. 2 over 3. And then, what is the answer? It is 3 over 5. And that is the answer here. So now let's take a look at the options. This is 3 over 5. That is the correct answers. None of these. So this one is also new. I hope you understood how you can do this one. But up to this point, you might wonder, why do we need to use this? Or where does this come from that if I have kinetic energy of translation, you can write 1 instead. If you have kinetic energy of rotation, you can just write C instead. Well, it comes from this. You remember first question that we had this. Let's just say, watch this one here instead. If I want to find the ratio of kinetic energy of translation of kinetic energy of rotation, see, kinetic energy of translation of it is equal to what? We just said that, if you remember. Let's just write kinetic energy of translation here. Instead of rotation here, I think I've told you, yes. No, all right, so kinetic energy of rotation, it is equal to C times translational kinetic energy, right? So these two cancel out. So what is left now? It is 1 over C. So these are where it comes from. But this is only true if we have ratios, because in ratios, these two will cancel out. What if you don't have the ratios? You can never use this. So be careful. And that is for that. There is one more question. I believe we approached, or we are at the end of this chapter now. There is one more question which I would like to solve for you guys. That also has an idea in this one too. So let's get back to this. These are the section review. Perhaps maybe I should have left this one for another session, but okay, since we did it. Standardized test preparation. There's one more question. Let me go through these questions real quick. It says the 3 forces acting on the wheel 3 forces acting on the wheel above have what? Have equal magnitude. Which force will produce the greatest torque on the wheel here? You can see that these 3 forces, if this is the radius, each one of them produce or act at a certain distance here. So because this force is perpendicular, this one produced the largest torque in here. This one produced no torque because there is, or you can say, is passing through, what am I saying? It's passing through the axis of rotation. This one, it is at some angle, so of course it is less than this one here. So we can say it is F1 produce the largest torque. Second part says if each force is 6 Newton and the angle between F1 and F2, this is also new here. If the angle is between F1 and F2 is 60 degree here, and 60, and the radius of the wheel is 1 meter, this is 1 meter, the question says what is the resultant torque on the wheel, like what is the net torque here? We have 3 forces, so there's supposed to be 3 torques, torque 1, torque 2, and torque 3. We can say torque 3 is 0 right away because it is passing through the axis of rotation. What about torque 1? We can say force times the distance. The force is 6, the distance is 1, so just 6 Newton meter. But which way is it rotating here? You can see that it's counterclockwise, so it is positive. What about the second torque here? Because we have angles, so FD times sine theta here, but you really have to be careful. 6 times the distance is 1 times, watch this. We said the distance must always be with what? The distance must always, the angle must always be with the distance here. So you need to find this angle right here, because this is given here, but that is not with the distance. So, but we know that the whole thing is right angle, okay? If this is 90, the whole thing is 90. If this is 60, what is this angle? 30, and that's it. So we can say sine 30. We know that sine 30 is half of 6 is going to be 3 Newton meters, the same direction. So now what is the total? The total torque, you add them all together, torque 1 plus torque 2 plus torque 3. That is going to be, if I add them here, 6 plus 3 plus 0, That is 9 Newton meter, but which way? It is counterclockwise, or you can say positive, and this is positive here, so the answer is C. And this is the solution here. Now, question 3 says, this one is also a bit interesting. Of course, there's a little bit actually, okay, I think I should not talk about the thing here. It says, if the same torque is applied to 2 pulleys of the same diameter to rotate with a different angular speed, then, so we have 2 pulleys that they have the same diameter. We have 2 pulleys that have the same diameter. Basha? Okay, let's bring the whiteboard. There are 2 pulleys. They have the same diameter. That's one. And this is the second. Okay, so we are applying the same torque in each one of these, let's say, or applying the same torque in here, same torque. Okay, but one of them, of course, will end up having a larger angular speed than the other one. Okay, one of them would end up having a larger angular speed than the other one here. Okay, so what is the question here? Rotate with different angular speed, so one of them is larger than the other one. The question says their moment of inertia are different. Their moment of inertia is different. Part B says their moment of inertia are equal. C says their rotational kinetic energy are different. Well, one easy way to get away with that, we can say option C is correct, because we know that kinetic energy of rotation, that is equal to 1/2 moment of inertia times angular speed squared, yes? So if they have different angular speed, then clearly their kinetic energy of rotation would be different. So that is one correct answer. But let me tell you something, but don't tell anybody else, okay? Basha, we know that if we apply the same torque on this based on Newton's second law of motion, Basha, torque the moment of inertia times angular acceleration, yes? If they have different angular speed, that means there will be different angular speed, yes or no? Basha, if we use the same torque, all right? If we use the same torque and they get different angular speed, right? Imagine if I go back to perhaps, let's expand this one. Yalla. Newton's second law of motion. Let's say I have a mass of, all right, let's say I apply a force of 10 Newton on an object in here. One of the object accelerates with 2 meters per second squared, let's just say. Okay, the other object, I'm using, like for example, the same force, which is 10 on the second object, but the other object would accelerate with, let's say, 4 meters per second squared. Basha, if they get different acceleration while I apply the same force, doesn't that mean they must have different masses here? Yes? Isn't that what it makes sense? Because the only thing that is different, it should be what? Their moment of inertia must be different. Okay, now let's go back to our example. If we use the same torque, Basha, but we get different angular speed, which means different angular acceleration too here, that is the case. Well, if I get different angular acceleration, but we use the same torque in here, Basha, doesn't that mean their moment of inertia must be different? Well, that's a good point, right? But let me tell you something even crazier than this. Have you noticed option A and B? Option A says their moment of inertia, or their moments of inertia are different. But part B says their moment of inertia are equal. Well, can you tell me which one is it now? Aren't they supposed to have different moment of inertia? Basha, if it is not different, aren't they supposed to be the same? It is either different or they should be the same, right? So this question has a little bit of confusion actually. If this question ever came in Wazari, it has to clarify, by the way. If not, you could just go ahead and choose C instead, because that's what the answer key, that's what they have chosen. It's been in Wazari once, right? C is considered as a correct answer for some reason, so we'll just pretend it is only C. But don't forget this too, right? So they have, or, like, I think the less you think about it, the better. Just remember, if this came in Uzadi, you can choose C. And that's it for now. Hopefully, unless if there's an update regarding this question, then the answer can be both C and A. But up to this point, there's no update. We can just consider C to be the correct answer. Question 4 says, which rotational quantity is equivalent to mass? I believe you already know that. That is moment of inertia, right? That's B. A force of this much, these are nothing new. I'll leave these on you guys here so that you can practice. What I wanted to solve is this question right here. Remember this. This is the same as for kinetic energy of rotation, translation, these stuff. But be careful. It is not a ratio. If it is not a ratio, we cannot use 1 and C's in here. Okay, so see what it says. The question says, we have a disk of mass. So there's a disk. It says a disk of mass, it's been in Wizard as well, 0.5 kilogram and a radius of this much. So let's write these information down. We have a mass, or first of all, a disk, which is moment of inertia is 1/2 mass times radius squared. The mass is 0.5 kilogram. The radius is 0.1 meter. Rolls without slipping on an inclined plane. What is the total kinetic energy? What is what? The total kinetic energy of the disk at an instant when the instantaneous speed of the center, it is 1 meter per second. Okay, so the question says, what is the total kinetic energy of the object when the instantaneous speed, that is translational, it is, look at the unit, is 1 meter per second. Yeah, Basha, how do you find this? Once again, that's a very easy method to do this. But because it is not a ratio, we cannot use what we have 1 and C before. So we can say total kinetic energy, that is equal to kinetic energy of translation plus kinetic energy of rotation. But we can still use this, Baba, don't forget. We said kinetic energy of rotation, you can write C times translation here instead. We can still use this one now. So once again, kinetic energy of translation plus, I'll write C times kinetic energy of translation. Instead of rotation, you can write C times translation instead. Now you can see that I have this 2 as a common factor. So I'll take kinetic energy as a common factor here. It is equal to, what is left here? 1. What is left on the other term? Just C. Now, of course, you can simplify kinetic energy of translation, which is 1/2 times mass times translational 1 plus, what is C for a disk? Isn't that 1/2? We only need the mass and the velocity now. 1/2. The mass is 0.5 times 0.5 times 1 squared. That doesn't change anything because it's 1. 1 plus, can I say 0.5? Yes. So let's just do this. And that'll be it. 0.5 times 0.5 times, actually, you don't have to say 1, times 1.5. The answer is going to be 0.375. 0.375. What is the unit of energy? It is in joules, and that is the answer. So which one is it now? Option A, B, C. It is option A. See, so the only idea, because it is not a ratio, I cannot use 1 and C, just 1 and C, for example, here. Now, but I can still, instead of using rotation, I can still use C times translation, which makes it a lot easier to do this one and in very, very, let's say, short steps. I believe that's the end of this. The remaining questions are nothing much, I guess. Let's just go through them anyway. It says, can 2 spheres of different diameter and different masses have the same moment of inertia? Yes, but how can this ever happen? 2 spheres of different diameter and different masses. Watch this. Moment of inertia is equal to shape factor times mass times the radius squared. Yes, that's for one of them. And then for the other one is going to be, let's say, different shape, mass and radius. Watch this, Baba. because the radius is squared, just imagine if one of them has 2 times the radius, that would be what? A total of c times mass, or let's just say this, c times mass times 4 times radius squared 1, yeah? Now, in order for the other one to be the same as this, by what factor should the mass of the other one should be smaller in this case? If the radius of this one is, for example, 2 times bigger than this, then the mass of the same object, of course, has to be 4 times less. 4 times less, so that this 4 and 4 cancel out. So these two both will end up having the same what? Having the same moment of inertia. You can do that by using one equation. I believe it would be even way simpler here. So now you can see that the mass of this one must be 4 times larger than the mass of this one. But the radius of this one, it is 2 times larger than the radius of this one. You might say, why 2? Because this is squared, and 4, because this is what it is. So if you use one equation, perhaps makes way easier here. Moment of inertia of 1, c times mass times radius squared in here. Like I said, what if the mass of, watch this, what if the mass of this one is 4 times larger than the other mass? Well, how do you cancel out the effect of this one? Then at this point, the radius of this must be 1/2 here, smaller than the radius of the other one. Because now, if you open this 4 times, or c times 4 times mass times, if you square this to that, it'd be 1/4 times radius squared. Then you have to use numbers that they always cancel out. Then we can say, then the moment of inertia of the two objects will be the same, even though they could have different mass and radius. So the answer is yes, if the mass of the second object is 4 times the first, but the diameter and the radius, of course, because you divide them by 2, so they have the same effect, it has to be 2 times, or half of the first object by using this equation right here. So whatever it is, right, it has to be inversely proportional, so you could do the numbers right. In which case would the angular momentum be conserved? We've mentioned that when the net external torque acting on the object is 0. Does the conservation of angular momentum lead to the conservation of rotational kinetic energy? The answer is no, because work may be done, and this work will be converted to rotational kinetic energy. Then the angular speed will not be conserved. And I would love to see you try these questions as well. And that is the end of this chapter. Even though this session was a little bit longer, but I hope you understand the reason why I just didn't want to leave the other, or these part for the next session. And I would recommend you solve these without any questions. There are about 60 questions, perhaps. I believe if you practice them, I can tell you that you've mastered all the concepts that is in this chapter. Till then, till another video session, or perhaps chapter 3. Stay tuned. I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.